And the half-life of carbon 14 is like 11,000 years. So after 11,000 years, half of your carbon 14 will become nitrogen 14. The important point here is isotopes are important, and they're used both medicinally and to help us date organic material. The actual process is a little bit less important. Okay. Atoms are, by themselves, somewhat interesting. But what we can do is we can take atoms and we can stick them together in interesting ways and make molecules. And molecules are much more interesting than atoms in independence are. So molecule is any set of atoms, 2 or more, that are connected by some chemical bond. And there are 4 types of chemical bonds that I'm going to want you to be familiar with, and their relative strength. The first type is called an ionic bond. So we were already familiar with this word, right? Ion. What is an ion?
Atoms that have only 2 protons?
Yeah. Some atoms that carry a charge, right? And an ionic bond is one in which 2 atoms that have opposite charges are connected to each other. So a positively charged ion, a cation, is attracted to a negatively charged ion, an anion. Now there's a really, really common ionic bond that we're going to diagram. So if sodium doesn't carry a charge, how many electrons does it have?
23.
11, right? So it has, we know that sodium has an atomic number of 11, and if it's got no charge, it has 11 electrons. Right now we have 10 electrons in this sodium atom. Where's that 11th electron going to go? Yeah, in the 3rd shell, right? And it's going to be all by its lonesome. It's just going to be sitting out here. This is a super unhappy state for sodium. Having a single electron in an energy shell is bad. There's another element called chlorine, and it has an atomic number of 17 and an atomic mass of 35, not 38. So chlorine has how many protons? 17. And it has how many neutrons?
18.
It's close to 35. Remember, that's the atomic mass, which is the protons plus the neutrons. What plus 17 gives you 35?
18.
18. So it has 18 neutrons. Are we okay with that so far? How many electrons does it have?
17.
17. And how many go into the first shell? How many go into the second shell?
8.
Which gives us so far how many? 10. Which leaves us with 7. So, just like this is a super unhappy state, having 1 extra electron or 1 electron in an energy shell, this is also a super unhappy state. Missing just 1 electron. Right? I mean, how would you like to be that person at the club where everybody else is paired up and you're just off by your lonesome? Nobody likes that, right? So really what you want to do is you want to find that one a partner. There was a question over here somewhere. Yeah, Mac.
Forgive me if you've already said this, but if the outer shell contracts the most energy, right? How come it's a bad thing if it's by itself?
They just don't like to have a single electron in its outermost shell. And we measure that by how likely it is to give up that electron.
Okay.
Yeah. So I like the way that you're thinking about it because, like from a biological standpoint, having more energy in that atom is a really good thing, right? Atoms, however, tend towards stability. What they want to do is increase their stability, and that requires reducing the amount of energy that they have. Okay. So, can you guys see where we're going with this? Right? What's going to happen is this electron that occupies its own space is going to jump ship. And it's going to come over here and pair up with that electron. Or excuse me, with that in that electron shell. So all of a sudden, sodium loses an electron. What does that do to its charge? Makes it positive, right? Because it lost an electron. So all of a sudden, sodium is carrying positive charge. What does that do to chlorine? Makes it negative. Now, what we know about electrical charges is that opposite charges attract, right? So we have a single positive charge, single negative charge, and those two atoms just naturally stick together. Makes what? NaCl, which is sodium chloride, which is table salt. Yeah, this is all table salt is. It's just a sodium ion attached to a chlorine ion. Does salt dissolve well in water? Super well. I mean, that's why the ocean is as salty as it is, right? Because it dissolves so incredibly well. The question that we need to start asking ourselves is, why? What is it about water that dissolves sodium chloride? You know, when it's dry, sodium chloride is incredibly stable. You can go to Peru, I believe it is, up into the mountains, and there's this rad cathedral that is excavated out of the mountain, and all of like the pews and the pulpit are all carved out of salt. It's just salt. And it's been stable for, it's rad, right? I mean, it's super cool.
Wouldn't that suck on a rainy day?
It probably would, right? You don't want to take a soda down there and spill it, right? Because it's all going to dissolve. But it's existed like that for hundreds and hundreds of years. When it's dry, sodium chloride is incredibly stable. When it gets wet, it dissolves really, really fast. Okay, so that's an ionic bond. It's two atoms that are attached to each other by a negative and a positive charge, or charge differential is how we refer to that. Okay, yeah?
So when you're writing this, so you made the diagram, you want to write sodium chloride, or you just write NaCl?
Mm-hmm. Yep, the chemical formula, that's what you're referring to, would just be NaCl, like that, sodium chloride. Do you guys think you could diagram that on an exam? If I said, show an ionic bond between sodium and chlorine, I think you guys should be able to diagram that on an exam, which means it's likely that's going
to be on the exam.
So just to make sense, let's talk about it a little bit. What questions do you have?
I have a question.
Okay, yeah.
So does that one electron go over, or like the whole thing like moves over? It's just like one electron.
That one electron jumps ship so that it's no longer circling around
and
sodium.
it pairs up again.
And it goes over there and it's paired up with chlorine. Yep, and then yep.
How do you show on like the exam that it jumped ship onto a different one?
I think you should just do exactly this.
Just put an arrow?
Boom. Yep.
Okay, so if you move like two of them over, would that be like two positives?
Yeah,
And then like two negatives?
it would. It would indeed.
So if one shell was missing two, well, one only had two and the other one was missing two, that would create a perfect bond because then people
They
would
completely
hate
satisfy each other, right?
Mm-hmm.
That's like soulmates. They complete each other. Yeah.
What would happen if this one was full and this one had a missing one? Would they even connect at all?
They wouldn't.
Okay.
I mean, if this was full, it's
That's what I
happy,
was thinking.
right?
Yeah.
You achieve the octet.
Yep.
So
Okay.
like,
Yeah.
how do you know like that's a positive and that's a negative?
Wonderful question. Why is this positive?
Like couldn't it be the other way around? Is it-
So let's do this. Let's actually show that this electron has jumped ship and is no longer associated with sodium. Oh, you are? Okay. This is how I unerase. Boom.
It's okay, I got it right here. So you can say.
Boom.
Okay, we okay?
Yeah.
Okay, so re-erase like this.
Wait, what are you doing? Why are you doing
So we're showing how it is that we know that something is actually positive
Oh, okay.
instead of negative, right?
Mm-hmm.
Okay, so how many, according to this diagram, how many protons does that atom have? Protons.
Oh.
It's close to 10.
11.
It's close to 10. It's 11, right? Because protons, which occur in the nucleus, are 11. How many electrons does it have? It's close to 11. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has one fewer electron than proton. What does that mean about its charge?
Positive.
It's got to be positive, right? Because it has more protons. Conversely, if that electron actually came over here, which it will, because I'm diagramming it, we can count a relative number of protons and electrons here as well, right? How many protons does it have? 17. If it was neutral, how many electrons would it have? Also 17. But it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. One more electron than proton. And electrons carry a negative charge, so that makes it inherently negative. Cool? Okay, other questions about this? I'm really glad that you guys are asking questions. Generally speaking, students don't, and then they just bomb this part of the test. Yeah?
Can I use my cell phone to take a picture?
Yeah, go right ahead. You want me to stand in it?
Sure.
Or just get it?
That makes it even better.
I'm gonna move, and y'all can hop up at your seats and take pictures of that if you want, so that you don't have people's heads, and that wouldn't bother me. Okay, so another type of bond is something called a covalent bond. Covalent bonds are cool because these occur between two atoms or more atoms that don't actually want to give up electrons. Rather, they would like to share electrons. Here, with ionic bonds, they're completely giving up an electron. This electron is never going to come back to sodium. It's now part of chlorine. It just lives with chlorine. But with covalent bonds, we actually have electron sharing. So the nature of that covalent bond is really determined by how many electron pairs are being shared. Sharing a single pair of electrons is a single bond. 2 pairs of electrons is a double bond. 3 pairs of electrons is a triple bond. Those are pretty uncommon. There's a really common molecule that enters into covalent bonding. And it includes our oxygen atom. So oxygen, excuse me, has an atomic number of 8 and an atomic mass of 16. Okay? So what that means is, in its nucleus, it has how many protons?
8.
8. And neutrons, it has
8.
also 8. Because 8 plus 8 equals 16. Now if it carries a neutral charge, how many electrons does it have?
8.
8 as well. 2 go into the first shell,
6.
6 into the second. I'm going to do it like this. How many electrons can it accept
2.
to fill its outermost shell? 2 more, right? So what would be really cool is if we could find an element that would be willing to give up 1 or 2 electrons. And there is an element, but it doesn't really want to give them up. There's an element called hydrogen, and hydrogen has an atomic number of 1 and an atomic mass of 1. Which is wacky, right? So how many protons does hydrogen have? 1. And how many neutrons does hydrogen have? 0, exactly right. Has no neutrons. How wacky is that? And then it has, if it's neutrally charged, how many electrons? It's close to 2. 1, right? Because it has 1 proton,
He never makes
so
me feel
each
stupid. He
1
always makes me feel
electron.
so much smarter.
So that's all hydrogen is. It's just a proton and an electron. And this is a really, really important element for us because our bodies take hydrogen and they rip electrons off and they pass protons around. It's really, really important. But what we know about that is that it's an unhappy state, right? That electron's just by itself. But hydrogen doesn't want to just like give it up and be a lonely proton either. And so rather what it would do is share some time with protons, or excuse me, with oxygen. So oxygen is willing to share this electron with hydrogen, and hydrogen is willing to share this electron with oxygen. And so what you get is this orbit that now circles both atoms like that. So those pairs of electrons are now shared between oxygen and hydrogen. How many more electrons can oxygen accept?
1.
1 more, right? In fact, if another hydrogen atom comes along, that would be perfect.
So
it'd be
another
water.
hydrogen molecule.
Right?
So that would be another hydrogen atom, yep, came along.
H2O.
Hydrogen's going to share its electron. Oxygen is going to share its electron.
Yeah. Genius.
And now we've created what molecule?
Water.
Water, exactly right, H2O. So H2O is a product of 2 single bonds between 1 oxygen atom and 2 hydrogen atoms, right?
I don't know why I never knew this in chemistry. I took chemistry. I never could get it.
And water, as it turns out, has some really, really important characteristics that make it biologically important. The dogma that we've all been filled with since grade school, right, is that water is essential for life. And on this planet, that's absolutely true. Water is essential for life. And it's essential for life because of some of those cool physical properties that we'll talk about in a few minutes. Now, sometimes that sharing of electrons isn't always fair. There's some atoms that are called electronegative, that hog time with the electrons. And that's the case here. Generally speaking,